Hey everybody, this video is us getting into conservation of momentum. There is a lot to unpack here. We're going to see what it is and some examples. Okay? Now before we get directly into conservation of momentum and where that comes from and its big implications, we have to make sure we remember internal and external forces. We have to remember the idea of systems. As a reminder, a system is really just what you're looking at, whatever it is you're analyzing. Okay? It doesn't mean you have to write down what your system is on a piece of paper, but you need to be consistent based on whether or not you're looking at just a single object, multiple objects, and what I mean, you have to make sure you're being consistent, like applying whatever forces or whatever energies are acting on things. Now, if I have this scenario right here where I have the two masses attached by a string over a pulley, somebody might say, quite classically that, oh, my system, it's the two masses and maybe the pulley, okay? So these two forces right here, these tensions, they are inside my system. Just like if I held up a baseball, there are forces acting inside the baseball, like holding the molecules together. Those molecule forces are internal. The tension forces right here are internal to my system. Okay, if they're inside my system, whatever it is I'm looking at, they're internal. However, if this was my system right here, well, gravity, the force that's coming from the Earth, well, I did not include the Earth in my system, so therefore, if I was, say, looking at forces, these weight forces, those would be external because they are originating from the Earth, something outside of my system that is tugging on things, okay? So system is really just what you're looking at, but depending on what you are incorporating, you have to be careful in terms of forces, energies, anything like that. We're going to see that momentum is one of the things that are important to make sure we are understanding what is part of our system when we want to apply momentum and momentum conservation. Okay? So now, what exactly is momentum conservation and where does it come from? I have right here a diagram and it shows two things. Maybe they're like two billiard balls. I have this purple one I've labeled number 1 and I have this other one that I've labeled 2. So I have 1 and 2. They're moving towards each other. They're rolling towards each other. We'll ignore friction in this example. Okay, they're rolling towards each other. It looks like they collide, they slam into each other, and then they just kind of bounce off in the opposite direction. Okay? What are some things that I know are going on? Well, when these two things collide, there are forces acting on each other. The pink ball exerts a force on this kind of lime green ball. The lime green ball exerts a force on the pink one. By Newton's third law, these two forces are the same. They have to be. When one object exerts a force on the other exerts an equal and opposite force. So these forces are the same. That's what I have right here. What I'm showing you right here is that the forces on these two objects are equal and opposite to one another. That's why I have this negative sign. The time of impact also has to be the same. And that's just kind of by reasoning through what's going on. If this collision took, I don't know, half of a millisecond, well, it's half of a millisecond for both of them. If this pink ball is exerting a force for half of a millisecond on this green ball, well, by Newton's third law, it's the same force, and, they're in contact for whatever amount of time, that must be the same amount of time. The moment one object is leaving the other, well, that other one is also leaving it. So they have both equal and opposite forces and the same time. That means by our good old impulse equation, well, the forces are equal but opposite. That means their impulses are equal and opposite. T is the same, and their forces are opposite. That means I have this equation right here, and if I do this just a little bit further, okay, the change in momentum for object 1, that is the final momentum for object 1, and the initial momentum for object 1. And that's equal to minus, well, that's going to be the final momentum of 2, and the initial momentum of 2. I have this minus and plus because I carry through this negative, okay? And this, that should be a little not there. So this is the change in momentum for object 1, the change in momentum for object 2. If I maybe swung this to this side right here, okay, oh, and I forgot, there should be a little minus sign right here, right? Because mv minus mv naught. Okay, so that's a minus sign, and then I swung it to the other side. What would I have? I'd have mv1 plus mv2, the final momentum of 1 plus the final momentum of 2, equals the initial momentum of 1, that's what this thing is, swung over there, plus the initial momentum of 2. Oh, this is the final momentum of object 1 and object 2, and that's equal to the initial momentum of object 1 and object 2. Their momentums in the beginning are equal to their momentums at the end. Or said another way, their momentums in total are being conserved. Or you could think of it this other way. I have this other scenario. Let's imagine my whole system is the two objects. So the net force acting on my system multiplied by time, that's the change in momentum for the system. Now, these internal forces were just that. They were internal. There's nobody coming from outside and slapping either of these balls. So the overall net external force is actually 0. So 0 times t, that's 0. That's equal to the change in momentum for the system. Or said another way, the total momentum of my system is not changing. It's 0. Now, these derivations, I should say, are not super crucial, but they're getting to the same idea. If there's nothing external, if there's nobody coming around and interfering, the net external force on my system, if that's 0, there is no net external force, then the overall total momentum remains constant. The total momentum of my system is conserved. That means if I'm zooming in and looking at my two different objects, I have this equation that pops up that's comparing their initial and final momentums. Okay? So what does that mean? You can use this to your advantage when there is a collision taking place. What you have to make sure you do, and these 3 steps are crucial. Number 1, make sure you're aware of your system. Normally, it's just whatever the 2 objects are that you're talking about. In this case, what a classic way to do is, well, this object here, number 1, and this object here, number 2, I'd say they are my system. And then I would add up all their momentums before a collision. So right now, this object here, P1, has momentum in the beginning. This object, P2, has momentum in the end. That must be equal to their momentums after. Here's the final momentum of 1, here's the final momentum of 2. And I can set up an equation saying that these 2 momentums combined are equal to these 2 momentums combined. That's what these 2 steps are saying here. So just you kind of look at what's happening before some event occurs, and you add up their momentum. You look at what happens after the event. Maybe it's an explosion, maybe it's a collision, but you look at the momentums after, and you can set them equal to each other. One thing to keep in mind, and we'll see an example of this, sometimes things might splat and stick and combine. If you have that, if you have 2 objects that are just kind of wedged together, well, their momentum is still the mass times the velocity, but maybe like you're adding up the 2 pieces and setting that equal to the 2 pieces' velocities. So if things are moving and kind of combined together, well, you can almost treat them as one object. So that might be helpful in certain scenarios, okay? Now, there's still more information. Oh my gosh, there's a lot to unpack in this video. When we're talking about collisions, when we're talking about 2 objects, it is crucial that we recognize that 99% of the time, energy is not being conserved. We applied conservation of energy for single objects that were flying through the air or that were being pushed on by springs. We were not looking at things slapping into one another, colliding with one another, exploding into multiple pieces. We can use momentum conservation for everything that I just listed. You cannot use energy conservation. And that's because if you imagine this scenario, whether this is a car crash or maybe this is a blob of clay, when you have 2 things actually colliding, in real life, heat is produced, materials bend and they warp, and all of that is an example of work, forces, and displacements. And we know that if work is being done, all of those that I described would be non-conservative forces. That would mean that work isn't being conserved. That removes energy. Most of the collisions that we deal with are known as inelastic collisions. And inelastic collisions, well, it just kind of means maybe there's some energy being lost to friction or any other numerous possibilities. You cannot use conservation of energy you cannot use conservation of energy if you have an inelastic collision. Here is an example where you might say something like P1 initial, and here's P2 initial. Well, what's happening here? You might just call this P1 plus 2. You might write this as the mass of little m plus the mass of 2m times that velocity. That's what I meant in the last slide about how you could kind of treat sometimes things as one single object. If this is a blob of clay and it sticks, well, that's an example of an inelastic collision. The momentum at the end, well, these 2 things are just added up. multiplied by whatever their velocity is. Here, before they're stuck together, you would treat them as separate things, okay? But you need to recognize that most of the time, energy is not conserved, with one single exception. And it's purely a theoretical, almost a thought experiment more than anything else. In real life, things are always bending and warping. But there is one theoretical type of collision known as an elastic collision. This is a collision where the impact is perfect. The collision is perfect, so to speak. There is no energy loss. This does not exist in real life, okay? But it is a way for us to apply conservation of energy in this one type of example. You should not use energy conservation unless you are told that a collision is elastic. Okay, and then if that's the case, you could say the kinetic energy of this object before is equal to the kinetic energy of this object after. Okay, but only if the collisions are perfectly, or if they're stated as being elastic. Okay, if it doesn't say elastic, you cannot use conservation of energy, but you can use conservation of momentum. That's why momentum is really, frankly, a more powerful physics tool. You can use momentum conservation whether you have one thing or two things or 20 things, as long as there's no outside forces. Energy is really 9 out of 10 times, 99 out of 100 times, energy conservation can only be used for a single object as it's moving. With the exception, if you're told a collision is elastic, that means, well, it might not happen in real life, but we'll pretend that it could happen, and then you could use conservation of kinetic energy. All right? Let's look at some examples of setting up conservation of momentum. Okay, let's do that. So here I have an example. Maybe I have this I'll call object A and object B. So in the beginning, they're separate, okay, but object A, I don't know, maybe it's a blob of clay. It combines, and now I have A and B all smushed together. How would I set this up? Well, conservation of momentum says that the momentum in the beginning is equal to the momentum in the end. Sometimes this is written like this because we're dealing with a lot of subscripts. You might see this as P equals P prime. Some textbooks, some physicists, instead of having 1,000 different things in the bottom, they'll use this little prime. It looks like a little apostrophe. They'll use this little prime to represent the final amount. I'll stick with the subscripts right here for this video just because that's what I was using earlier. So in the beginning, what kind of momentums exist? Well, if A is moving, then A has some initial momentum plus some initial momentum of B. It looks like it's at rest, but whatever. That is equal to the momentum after. And in the end, it looks like the two things are combined. So what is classically written is something like this. So I might write down this is the mass of A times the initial velocity of A plus the mass of B times the initial velocity of B is equal to, well, the mass of A plus the mass of B times their final velocity. Okay, maybe you write that as V prime, okay, or whatever, just whatever that final velocity is. Now, vectors and direction is important. So if I say to the right is positive, I would have positive velocities here. And it looks like after it would have some positive velocity. But if B was moving to the left in the beginning, you would be subtracting this momentum. Okay, so you set up all the momentums before a collision or before an action. It looks like, first they're separate and then bam, they collide. And then you can look at the momentums after. Now there's no numbers here. There's nothing for me to plug in, but here's an example of me setting this up for two separate objects that slap into each other and then they are connected. Okay, you don't memorize these equations. What you memorize is, okay, I look at the momentum before. All right, well, this thing has momentum, so I got to write it out. I got to do mass times velocity. Maybe this thing has momentum. I multiply mass times velocity. And I set those initial parameters equal to the final parameters. Because there's a variety of different scenarios. Don't memorize this specific equation. That only applies for this specific scenario. Your process, okay, what is my system? Okay, it's this thing and this thing. What are the momentums before? Add them up. Set that equal to the momentums after. Add it up. Okay? Let's look at another example, and this one's a little different. Instead of starting off with two separate objects, I have two objects together. I have a gun and a bullet. And if you imagine a TV or a movie, you got a gun, you got it loaded, but it hasn't been fired yet. So both of these objects are starting at rest, and then bam, I fire the gun. And after I fire the gun, the two things are separate. How would I set up conservation of momentum for this? Well, it's still me looking at the total momentum in the beginning and setting it equal to the momentum in the end. in the beginning, I have, maybe I'd call this the mass of the gun, and then here is maybe the mass of the bullet. Oh, sorry, I have this yellow pen. It's not very good. But they start off together. So in the beginning, I have both the gun and the bullet. And then afterwards, I have the momentum of the gun and the momentum of the bullet. Okay? Again, I didn't memorize any particular equation. All I know is I add up all the momentums before, and I set that equal to all the momentums final. So here it would be, well, momentum is mass times velocity. That would be the mass of the gun plus the mass of the bullet. Oh, but they start at rest, so the velocity would be 0. I am ultimately going to have 0 on this left-hand side. And then on the right-hand side, well, the mass of the gun multiplied by the velocity of the gun plus the mass of the bullet times the velocity of the bullet. Now, the gun is going to be moving backwards to the left. So if I do my classic rightwards is positive, this is probably, I know I don't have a number to plug in, but this would probably be a negative value. And if you notice something, this is actually showing why, in fact, the gun has to go the other way. Stay with me. The initial momentum was 0 because both these objects started at rest. Well, if momentum is conserved, that means if I started with 0 momentum, I have to ultimately end with 0 momentum. And if the bullet is flying off to the right with some right momentum, if I have to add up to 0, it must mean that the gun is going to have momentum in the opposite direction. These objects have canceling momentum to get back to 0 total momentum. And I have to get back to 0 total momentum because that's what I started with. This is, in fact, why guns recoil. And if you're thinking, wait a minute, Mr. Thrasher, you use a similar explanation for Newton's third law, you're absolutely right. Now, you don't necessarily have to memorize this or anything, but Newton's third law, that weird for one force there's an equal and opposite force, Newton's third law is really actually conservation of momentum. This is kind of the proof more mathematically using momentum conservation. But what this signifies is that when there's one force to the right, if I started at rest, there must be a totally balancing force causing motion to the left in the opposite direction. But again, what's the key idea? I know this video is getting long. We're getting up to 18 minutes. But the key idea is, for these types of problems, when there's a collision or maybe there's an explosion, you think about what's going on before. What are the objects? Add up their momentum before. What's happening after? Okay, how many objects are there? And then you add up their momentums after. Okay, these are tough at first, like a lot of this class, but you get good with practice. And that's what you're going to be doing next time in my class, or whenever you crack open your textbook or your college papers and you start working on problems. But it's all about looking at the total momentum that objects have in the beginning, the total momentum that objects have at the end, and you can set them equal to each other. Okay? That's it for this video. Oh, what a long one. Thanks a lot for watching.